Welcome to Whispering Atom, where the gentlest mysteries of our natural world unfold like whispered secrets, and science becomes a peaceful companion for your evening journey toward rest. I'm so grateful you've chosen to join me tonight as we embark on a vertical voyage, not through the depths of space or the far reaches of time, but upward, through the layers of our own atmosphere, discovering how the very air we breathe transforms as it flows over mountains and rises toward the sky. As you settle in wherever you are in this wide world, I'd love for you to share where you're watching from tonight and what time your clock shows. Are you nestled comfortably in a valley somewhere, perhaps surrounded by gentle hills that rise toward distant peaks? Maybe you're already at elevation, where the air feels crisp and light against your skin. Or perhaps you're at sea level, breathing the thick, rich air that carries the weight of the entire atmosphere above you. Take a moment, if you'd like, to let us know in the comments where you are and what time it is in your corner of our rotating planet. There's something beautifully grounding about knowing we're all here together, breathing the same atmosphere, sharing the same ocean of air that connects every living thing on Earth. Now, get comfortable. Let your breathing settle into its natural rhythm. Feel your chest rise and fall with each gentle breath. Tonight, we're going to explore something that's happening all around us at this very moment. The quiet, invisible transformation of air as it encounters the solid earth, rises over mountains, and changes its very nature in response to the ancient dialogue between atmosphere and stone. We'll discover how pressure whispers its secrets to molecules, how temperature dances with altitude, and how the air that enters our lungs carries within it the story of every mountain it has crossed. Imagine, if you will, that you could somehow become aware of a single breath of air as it begins a journey that will take it from the warm, dense atmosphere at sea level, up and over a mountain range, and down into the valleys beyond. This isn't just any ordinary breath of air, but one that carries within it the experiences of countless molecules, each one responding to the changing conditions it encounters as it rises through the layers of our atmosphere toward the peaks that scrape the sky. Our breath of air begins its journey at sea level, perhaps over a calm ocean where the water's surface meets the sky in that perfect line we call the horizon. Here, at the bottom of our atmospheric ocean, the air is dense and rich, pressed down by the full weight of all the atmosphere above it. Each cubic foot of this sea-level air contains roughly 2.7 times 10 superscript 2 superscript 3 molecules, a number so large that if you could count one molecule every second, it would take you billions of times longer than the universe has existed to count them all. But numbers, vast as they are, don't capture the true character of this air at sea level. It's thick and substantial, carrying moisture from the ocean's surface, particles of salt that dance in the sunlight, microscopic droplets of water that will later become clouds, and all the gases that make up our life-sustaining atmosphere. When you breathe this air into your lungs, you can almost feel its richness, its density, the way it fills your chest completely and satisfies your body's need for oxygen with generous abundance. This sea-level air moves with a certain lazy confidence, flowing in broad, smooth patterns across the water surface. It's in no hurry to change, content to maintain its temperature, its pressure, its composition as it drifts with the gentle winds that characterize calm ocean conditions. The molecules within it bump into each other frequently, sharing energy, maintaining thermal equilibrium, creating the stable conditions that define air at the bottom of our atmospheric column. But then, something appears on the horizon that will change everything for our traveling breath of air. In the distance, the solid earth rises from the sea, creating the first gentle slopes that will eventually become foothills, then mountains, then towering peaks that reach so high they pierce the lower layers of the atmosphere itself. As our air encounters this rising land, it faces its first choice. It can flow around the obstacle, seeking the path of least resistance, or it can do what air so often does when it meets an immovable object. It can rise. The decision, if we can call it that, is made by physics rather than preference. As the moving air encounters the sloping land, it has nowhere to go but up. The solid Earth forces it to rise, molecule by molecule, carrying with it all the properties it acquired during its time at sea level: its temperature, its moisture, its density, its pressure. But as it rises, these properties will begin to change in ways that follow some of the most beautiful and fundamental laws of physics. The first change our ascending air experiences is so subtle that it would be imperceptible to human senses, yet it represents the beginning of a transformation that will affect every aspect of how the air behaves and how it impacts the living world around it. As the air rises just a few feet above sea level, the pressure surrounding each molecule decreases very slightly. This happens because there's now less atmosphere pressing down from above. The air has left behind a thin layer of the atmospheric column that was contributing to the pressure at sea level. This pressure decrease is gentle and gradual, following what scientists call the barometric formula, a mathematical relationship that describes how atmospheric pressure decreases with altitude in a predictable, smooth curve. For every foot of elevation gained, the pressure drops by a tiny but consistent amount. At first, this change is so small that even the most sensitive instruments would struggle to detect it, but it represents the beginning of a process that will eventually transform our sea-level air into something altogether different. As the pressure around each molecule decreases, the molecules respond by expanding slightly, taking up more space than they did at sea level. This expansion isn't dramatic. We're not talking about balloons inflating or sudden changes in volume. Instead, it's a gentle, gradual process where the average distance between molecules increases slightly as the external pressure that was squeezing them together relaxes its grip. This molecular expansion has immediate consequences for the density of the air. Density is simply the amount of mass contained in a given volume, and as the same molecules spread out to occupy more space, the density decreases proportionally. The air becomes lighter, less substantial, carrying fewer molecules in each cubic foot than it did at sea level. But our ascending air is still very close to sea level at this point in its journey, and the changes we're describing are barely detectable. The air still feels thick and rich, still carries the moisture and warmth it picked up from the ocean, still moves with the confident flow patterns that characterize low-altitude atmosphere. To a casual observer, this air would be indistinguishable from the sea-level air it was just moments before. Yet the process of transformation has begun, and it will continue with patient persistence as our air continues its upward journey. Each additional foot of elevation will bring another small decrease in pressure, another slight expansion of the molecules, another incremental reduction in density. These changes accumulate gradually, following mathematical relationships that have remained constant since the formation of our atmosphere billions of years ago. The beauty of this process lies in its gentleness and predictability. There are no sudden shocks or dramatic transitions as air rises through the lower atmosphere. Instead, there's a smooth, continuous change that allows living things to adapt, weather patterns to develop gradually, and the air itself to maintain its essential character, even as its properties slowly evolve. As our air continues its ascent through what we might call the coastal foothills, now perhaps 100 feet above sea level, the pressure has decreased from a standard sea level value of 14.7 pounds per square inch to something very slightly less, perhaps 14.68 pounds per square inch. This difference is so small that human senses can't detect it, but it represents a measurable change in the physical state of the atmosphere. The temperature of our ascending air remains essentially unchanged at this low elevation. Temperature changes in rising air follow different physical laws than pressure changes, and at these modest heights, the cooling effects that will become important later in our journey haven't yet begun to manifest significantly. The air retains the warmth it acquired from contact with the ocean's surface, carrying that thermal energy upward like a gift from the sea to the mountains. The moisture content of the air also remains stable during these early stages of ascent. The water vapor that evaporated from the ocean's surface continues to travel with our air mass, invisible but present, waiting for the changing conditions at higher elevations to transform it into the visible phenomena we call clouds, fog, or precipitation. At this low altitude, the air can still hold all the moisture it acquired at sea level, maintaining the humidity that will play such an important role in the atmospheric processes we'll explore as our journey continues. The winds at this elevation flow in patterns that are still strongly influenced by large-scale atmospheric circulation rather than the local topography. Our air moves in broad, smooth currents that follow the pressure gradients and temperature differences created by the heating of the Earth's surface and the rotation of the planet. These winds carry our air mass along with millions of other parcels of air, all beginning their own vertical journeys as they encounter the rising landscape. As we observe our air at this early stage of its mountain encounter, we can appreciate the remarkable stability and resilience of atmospheric systems. The air doesn't struggle against the topography that forces it upward, doesn't resist the changes that altitude will impose upon it. Instead, it responds with fluid grace to the physical laws that govern its behavior, beginning a transformation that will demonstrate some of the most beautiful principles of atmospheric physics. The molecules that make up our ascending air are in constant motion, vibrating, rotating, and translating through space in the random molecular dance that characterizes all gases. But this apparent randomness follows statistical laws that create predictable bulk behavior. As pressure decreases with altitude, the average kinetic energy of the molecules remains the same, but they spread out to occupy more space, creating the density changes we've been describing. This molecular perspective reveals another layer of beauty in the atmospheric processes we're exploring. Each individual molecule follows its own random path, bouncing off its neighbors, changing direction and speed in unpredictable ways. Yet when we consider the behavior of trillions of molecules together, their collective response to changing altitude follows precise mathematical relationships that allow us to predict and understand atmospheric behavior with remarkable accuracy. The electromagnetic properties of our ascending air also remain essentially constant at these low elevations. The air continues to interact with sunlight in the same ways it did at sea level, scattering blue light to create the sky's familiar color, absorbing and re-emitting infrared radiation to maintain thermal equilibrium with its surroundings. These optical properties will become more important as our air rises to elevations where the thinner atmosphere creates different conditions for light interaction. As our air approaches the first significant rise in elevation, perhaps the beginning of what we might recognize as foothills, we can sense that we're approaching a transition point where the changes we've been describing will begin to accelerate and become more noticeable. The pressure will continue to decrease, but now at a rate that sensitive instruments can easily detect. The density will continue to diminish, but now by amounts that will begin to affect how the air behaves and how it interacts with the landscape around it. The winds will begin to show the first signs of topographic influence, as the rising land forces the air to flow in patterns that are shaped by the contours of the Earth's surface rather than just the large-scale atmospheric circulation. The temperature will soon begin to show the first hints of the cooling that will become one of the most important aspects of our air's transformation as it climbs toward higher elevations. But for now, as we prepare to follow our air into the foothills and beyond, we can rest in the knowledge that we're witnessing one of the most fundamental and reliable processes in the natural world. The interaction between air and mountains has been occurring for as long as both have existed on our planet, creating the weather patterns that shape ecosystems, the winds that carry moisture from oceans to continents, and the atmospheric conditions that make life possible in the remarkable diversity of environments we find on Earth. Our ascending air carries within it the potential for clouds and rain, for winds and weather, for the countless atmospheric phenomena that will unfold as it continues its journey over the mountains. But it also carries something more fundamental. It represents the endless circulation of our atmosphere, the constant mixing and movement that keeps our planet's air fresh and life-sustaining, connecting every place on Earth through the shared medium of our common atmosphere. As we prepare to follow our air higher into the foothills, we can appreciate that we're beginning a journey that will reveal some of the most beautiful and essential processes of our planet's atmospheric system. The changes that lie ahead in pressure and temperature, in density and humidity, in wind patterns and moisture content. All follow laws of physics that operate with the same reliability, whether we're watching a single breath of air or the vast atmospheric currents that circle our globe. In the chapters ahead, we'll explore each of these changes in detail, discovering how the simple act of rising in elevation triggers a cascade of physical processes that transform our familiar sea-level air into something altogether different and remarkable. We'll learn how mountains shape the air that flows over them, and how that shaped air, in turn, creates the conditions that support the incredible diversity of life we find in mountain environments around the world. As our breath of air continues its gentle ascent from the coastal plains into what we now recognize as true foothills, we begin to witness the first measurable changes in its character and behavior. The elevation here might be anywhere from 500 to 2,000 feet above sea level, modest heights by mountain standards, but significant enough that our traveling air mass starts to exhibit the properties that will define its transformation as it journeys toward higher peaks. The landscape around our ascending air has taken on a different character now. Gone are the flat expanses and gentle rolling hills of the coastal regions. Instead, the earth rises in more pronounced slopes, creating valleys and ridges that channel the wind in new patterns. Forests may clothe these hillsides, their canopies creating a textured surface that interacts with the moving air in complex ways, sometimes slowing its passage, sometimes accelerating it through natural wind tunnels formed by the topography. At an elevation of perhaps 1,000 feet, our air encounters its first really noticeable change in atmospheric pressure. Where the pressure at sea level was 14.7 pounds per square inch, here it has dropped to approximately 14.2 pounds per square inch. This might not sound like a dramatic change, but it represents a reduction of about 3.5%, enough to create measurable effects on both the physical properties of the air and the biological systems that depend on it. This pressure reduction occurs because our air has now left behind a substantial column of atmosphere, roughly 1,000 feet worth of air that was contributing to the pressure at sea level. Think of atmospheric pressure as the weight of all the air above any given point. As our air rises, there's less and less atmosphere above it to create that downward pressure, so the molecules around it can spread out more freely than they could at lower elevations. The decreased pressure allows the air molecules to expand, increasing the volume they occupy while keeping their total mass the same. This expansion results in a corresponding decrease in air density. Where a cubic foot of air at sea level might contain those 2.7 times 10 superscript 2, superscript 3 molecules we mentioned earlier, the same cubic foot at 1,000 feet of elevation contains noticeably fewer, perhaps 2.6 times 10 superscript 2, superscript 3 molecules. The difference might seem small in percentage terms, but it represents billions upon billions of fewer molecules in every breath. For most people, this density change at 1,000 feet is barely noticeable. You might take slightly deeper breaths without realizing it, or feel a very subtle difference in how the air feels as it enters your lungs. But the change is gentle enough that healthy individuals adapt to it almost unconsciously. The human body is remarkably resilient and adaptable, capable of adjusting to these modest changes in air density without any particular effort or discomfort. However, sensitive instruments can easily detect these changes, and they provide our first real measurements of how air transforms with altitude. Barometers show the pressure decrease, while devices that measure air density reveal the corresponding reduction in molecular concentration. These measurements follow predictable mathematical relationships that atmospheric scientists have been studying for centuries, creating precise models of how air behaves as it rises through the atmosphere. The temperature of our ascending air remains relatively stable at these moderate elevations, though careful measurements might detect the beginning of a very gradual cooling trend. Temperature changes in rising air are governed by different physical principles than pressure changes, and the cooling effects that will become dramatically important at higher elevations are just beginning to manifest at foothills altitudes. The reason for this temperature stability at lower elevations relates to the heat capacity of air and the relatively small amount of expansion that has occurred so far. When air expands as pressure decreases, it does work against the surrounding pressure, which tends to cool it slightly. But at these modest elevations, the expansion has been small enough that any cooling is largely offset by heat absorbed from the surrounding environment. The warm earth, solar radiation, and thermal energy radiated from vegetation and rock surfaces. The moisture content of our air remains essentially unchanged as it passes through the foothills. The water vapor that evaporated from the ocean's surface continues to travel with the air mass, invisible and stable at these elevations. The air's capacity to hold moisture is determined primarily by its temperature. And since the temperature hasn't changed significantly, the relative humidity remains roughly constant even though the air density has decreased. This stability in moisture content is important for understanding why the first stages of a mountain crossing don't typically produce dramatic weather phenomena. The air may be getting slightly less dense, but it's not yet cool enough to force water vapor to condense into visible droplets. The dramatic cloud formations, rain, and snow that we associate with mountain weather typically occur at higher elevations where temperature changes become more pronounced. The wind patterns in the foothills begin to show the first clear signs of topographic influence. Instead of the broad, smooth flows that characterize air movement over flat terrain, the winds now follow the contours of the landscape, accelerating through valleys and passes, slowing as they encounter ridges and steep slopes. These topographic effects create the first hints of the complex wind patterns that will become increasingly important as our air continues its upward journey. Valley winds develop as the sun heats the slopes differently throughout the day, creating thermal currents that rise from sun-warmed south-facing slopes and sink along cooler north-facing hillsides. These local wind patterns interact with a larger-scale atmospheric circulation, creating complex flow patterns that can channel our ascending air in unexpected directions or concentrate it in particular valleys or passes. The vegetation in the foothills also begins to show subtle adaptations to the changing atmospheric conditions. Plants at these elevations might be slightly different from their sea-level cousins, with modifications that help them cope with the marginally lower air density and the beginning effects of topographic wind patterns. Trees might have slightly smaller leaves, stronger root systems, or other adaptations that help them thrive in the transition zone between coastal and mountain environments. Animal life in the foothills provides another window into how living systems respond to changing atmospheric conditions. Many animals move freely between sea level and foothill elevations without apparent difficulty, their respiratory and circulatory systems easily adapting to the modest differences in air density. However, careful observation might reveal subtle changes in behavior, perhaps birds flying with slightly different wing beat patterns or mammals breathing a bit more deeply during strenuous activities. As our air continues its ascent through the foothills, passing perhaps from 1,000 to 3,000 feet in elevation, the changes we've been describing gradually intensify. The pressure continues to drop following the same mathematical relationship, reaching approximately 13.2 pounds per square inch at 3,000 feet, a reduction of about 10% from sea level values. This more substantial pressure change begins to create effects that are noticeable even to casual observation. The air density at 3,000 feet has decreased proportionally with the pressure, creating conditions where each breath contains noticeably fewer molecules than the same volume would contain at sea level. For most healthy individuals, this is still well within the range of easy adaptation, but sensitive people might begin to notice that they need to breathe slightly more deeply or more frequently during physical exertion. The expansion of air that occurs as pressure decreases with altitude follows a fundamental principle of gas behavior known as Boyle's law, which states that the volume of a gas is inversely proportional to the pressure exerted on it, assuming temperature remains constant. As our air rises and pressure decreases, it expands to occupy more space, which directly causes the density reduction we've been observing. This expansion process is perfectly smooth and predictable, following mathematical relationships that allow atmospheric scientists to calculate exactly how air density will change at any given elevation. There are no sudden transitions or discontinuous changes, just the steady, gradual response of air molecules to the decreasing pressure that accompanies increasing altitude. The temperature of our air begins to show more noticeable changes as it reaches the higher elevations of the foothills. The cooling that was barely detectable at 1,000 feet becomes measurable at 3,000 feet, though it's still quite modest, perhaps a decrease of 3 or 4 degrees Fahrenheit compared to sea level temperatures. This cooling occurs because the expanding air does work against the surrounding pressure, converting some of its thermal energy into mechanical energy in the expansion process. This temperature decrease with altitude is the beginning of what atmospheric scientists call the adiabatic lapse rate, the rate at which air temperature decreases as air rises and expands in the atmosphere. At these moderate elevations, the lapse rate is relatively small, but it represents the start of a process that will become increasingly important as our air continues toward higher elevations where the temperature changes become dramatic enough to drive major weather phenomena. The slight cooling that occurs at foothill elevations also begins to affect the air's capacity to hold moisture, though the effects are still modest. Cooler air can hold less water vapor than warmer air, so as our ascending air cools, it approaches the point where it will be saturated with moisture. However, at these elevations and with these small temperature changes, the air is still well below its saturation point, so the water vapor remains invisible and stable. The interaction between our ascending air and the increasingly complex topography of the foothills creates the first examples of orographic effects, changes in weather and wind patterns that are caused specifically by the presence of mountains and hills. These effects are still relatively subtle at foothill elevations, but they provide the first hints of the dramatic atmospheric phenomena that occur at higher elevations. As air flows over hills and ridges, it accelerates on the windward side and may create areas of turbulence or wind shadow on the leeward side. These effects can concentrate moisture in particular areas, create local variations in temperature and humidity, and establish the foundation for the more complex weather patterns that develop as the topography becomes more dramatic at higher elevations. The biological systems in the higher foothills begin to show more pronounced adaptations to the changing atmospheric conditions. Plant communities may shift toward species that are better adapted to slightly lower air density, cooler temperatures, and the more variable wind patterns created by the topography. Trees might be shorter or have different growth patterns compared to their lower elevation relatives, while understory plants might show adaptations for dealing with the more variable light conditions created by the complex topography. Animal populations in the higher foothills often include species that are transitional between lowland and mountain forms, or that show behavioral adaptations for dealing with the changing atmospheric conditions. Birds might alter their flight patterns to take advantage of the topographic wind effects, while mammals might show subtle changes in their respiratory patterns or activity levels that reflect the decreasing air density. The acoustic properties of the air also begin to change noticeably at foothill elevations. Sound travels differently through air of different densities, and the lower air density at 3,000 feet means that sounds may carry differently than they do at sea level. The changes are subtle, perhaps a slight difference in how voices carry across valleys, or how bird songs sound in the thinner air, but they represent measurable effects of the atmospheric changes we've been exploring. Human visitors to foothill elevations often report a subjective sense that the air feels thinner or lighter, even though they may not experience any difficulty breathing or physical discomfort. This perception reflects the real physical changes in air density that we've been describing, translated into sensory experiences that our bodies can detect even when the changes are too small to cause physiological stress. The optical properties of the atmosphere also begin to show subtle changes at foothill elevations. The lower air density means there are fewer molecules to scatter sunlight, which can result in slightly different qualities of light and color. The sky might appear a slightly deeper blue, distant objects might seem clearer and more sharply defined, and the overall visual quality of the landscape might have a subtle crispness that's different from sea level views. As we prepare to follow our ascending air beyond the foothills toward the true mountain elevations where the changes we've been observing will intensify dramatically, we can appreciate how smoothly and gradually the atmosphere responds to changing elevation. There are no sudden shocks or dramatic transitions in these early stages of mountain crossing, just the steady, predictable response of air to the fundamental physical laws that govern gas behavior. The foothills represent a transition zone where the familiar atmospheric conditions of sea level gradually give way to the more dramatic changes that characterize high-altitude environments. Our air has begun its transformation from the dense, stable conditions of the coastal atmosphere to the thinner, more dynamic conditions that will define its experience at higher elevations. In the next phase of our journey, we'll follow our air as it encounters the steeper slopes and higher elevations where the changes we've been observing will accelerate and intensify, creating the conditions that drive the remarkable weather phenomena and ecological adaptations that characterize true mountain environments. As our traveling air mass continues its upward journey, leaving behind the gentle foothills and beginning to encounter the more dramatic elevations that define true mountain territory, we enter a realm where the molecular dance of the atmosphere takes on an entirely different character. Here, at elevations ranging from perhaps 4,000 feet to 8,000 feet above sea level, the changes in air density become not just measurable but transformative, creating conditions that affect everything from the way sounds travel to how living beings must adapt to extract the oxygen they need from an increasingly sparse molecular environment. At 5,000 feet of elevation, our air has undergone changes that would have seemed dramatic if they had happened suddenly, but which have unfolded so gradually during the ascent that they represent a smooth progression along well-understood physical principles. The atmospheric pressure here has dropped to approximately 12.2 pounds per square inch, a reduction of nearly 17% from sea level conditions. This isn't just a number on a barometer. It represents a fundamental change in the physical environment that affects every molecule of air and every process that depends on atmospheric density. To understand what this pressure reduction means at the molecular level, imagine the countless trillions of air molecules that surround us at any given moment as dancers in an enormous ballroom. At sea level, this ballroom is crowded, with dancers packed closely together, constantly bumping into each other, sharing energy and momentum in frequent collisions. As our air rises to 5,000 feet, it's as though the ballroom has expanded while the number of dancers has remained the same. Now there's more space between each dancer, fewer collisions, more room for individual movement. This molecular spacing has profound implications for how air behaves and how it interacts with the world around it. When molecules are farther apart on average, they exert less pressure on the surfaces they encounter. They carry less mass in any given volume. They conduct heat differently because there are fewer molecular collisions to transfer thermal energy. They transmit sound differently because acoustic waves depend on molecular interactions to propagate through the medium. The density of air at 5,000 feet has decreased proportionally with the pressure, dropping to about 0.086 pounds per cubic foot compared to 0.076 pounds per cubic foot at sea level. This means that every breath you take at this elevation contains roughly 17% fewer molecules than the same volume would contain at sea level. For your lungs, this translates to less oxygen available in each breath, less nitrogen to provide the bulk of atmospheric volume, and fewer molecules of all the trace gases that make up our complex atmospheric mixture. But the remarkable thing about this molecular thinning is how smoothly and predictably it occurs. There are no sudden gaps in the atmosphere, no regions where air molecules are missing entirely. Instead, the spacing between molecules increases gradually and uniformly, following the mathematical relationships that govern gas behavior under changing pressure conditions. The atmosphere remains continuous and complete, just less dense than it was at lower elevations. This gradual thinning creates what we might think of as a vertical gradient in the atmosphere, a smooth transition from the dense air of sea level to the increasingly sparse air of higher elevations. This gradient is so smooth that it can be described by precise mathematical formulas that allow atmospheric scientists to predict the air density at any elevation with remarkable accuracy. The temperature changes that accompany this molecular thinning add another layer of complexity to the atmospheric transformation we're observing. At 5,000 feet, our air has cooled noticeably compared to sea level conditions, perhaps 10 to 15 degrees Fahrenheit cooler than it was when it began its journey over the ocean. This cooling occurs because the expanding air converts some of its thermal energy into the mechanical work of expansion against the decreasing atmosphere pressure. This temperature decrease is governed by the adiabatic lapse rate, which describes how quickly air temperature decreases with altitude when no heat is exchanged with the surrounding environment. For dry air, this rate is remarkably consistent at about 5.4 degrees Fahrenheit per 1,000 feet of elevation. This means that our air, which might have started its journey at a comfortable 70 degrees Fahrenheit at sea level, has cooled to perhaps 55 degrees Fahrenheit by the time it reaches 5,000 feet. The cooling affects the molecular dance in important ways. Cooler molecules move more slowly on average, have less kinetic energy, and interact with each other differently than warmer molecules. Combined with the increased spacing due to lower pressure, this creates air that behaves quite differently from its sea level origins. The air is not only less dense, but also cooler, creating conditions that will increasingly challenge living systems as elevation continues to increase. The interaction between decreasing density and decreasing temperature creates complex effects on how air holds and releases moisture. Cooler air has a lower capacity to hold water vapor than warmer air. So as our ascending air cools, it approaches the point where it can no longer hold all the moisture it picked up at sea level. We're approaching the conditions where water vapor will begin to condense into visible droplets, creating the clouds and fog that are such characteristic features of mountain weather. At 5,000 feet, our air might still be below its saturation point, but it's getting closer to the temperature and pressure conditions where dramatic changes in moisture behavior will occur. The invisible water vapor that has been traveling with our air mass throughout its journey is becoming increasingly unstable, ready to transform into the visible phenomena that create mountain weather patterns. The acoustic properties of the thinner air at 5,000 feet create noticeable changes in how sounds behave in a mountain environment. Sound waves propagate through air by creating compressions and rarefactions in the molecular medium, regions where molecules are pushed closer together alternating with regions where they're spread farther apart. In thinner air, there are fewer molecules available to participate in this wave propagation, which affects both the speed of sound and how efficiently sound energy travels through the medium. Voices carry differently in thin mountain air. Sounds may seem clearer and more distinct because there's less molecular interference, but they may also seem to fade more quickly with distance because there are fewer molecules to maintain the wave propagation. The acoustic environment of a mountain at 5,000 feet has a distinctive character that experienced mountaineers learn to recognize. Sounds have a crisp, clear quality that's noticeably different from the rich, dense acoustic environment of sea level. The optical properties of the atmosphere also change dramatically as molecular density decreases. Light scattering depends on interactions between photons and air molecules, so thinner air scatters light differently than dense air. This creates the incredibly clear, sharp visual quality that's characteristic of high-altitude environments. Distant objects appear remarkably clear and detailed because there are fewer molecules between the observer and the object to scatter light and reduce contrast. The sky itself appears different at 5,000 feet. The blue color of the sky is created by the scattering of sunlight by air molecules, with shorter blue wavelengths being scattered more efficiently than longer red wavelengths. In thinner air, there's less scattering overall, so the sky appears a deeper, more intense blue than it does at sea level. At higher elevations, this effect becomes even more pronounced, eventually creating the deep, almost purple-blue skies that characterize very high mountain environments. Plant life at 5,000 feet shows clear adaptations to the thinner air and changing environmental conditions. Trees may be noticeably shorter than their lower elevation relatives, with smaller leaves and different growth patterns that reflect the challenges of photosynthesis and respiration in less dense air. Many mountain plants have developed larger root systems, waxy leaf coatings, or other adaptations that help them cope with the increased ultraviolet radiation and variable weather conditions that accompany high-altitude environments. The reduced air density affects plant physiology in complex ways. Photosynthesis depends on the uptake of carbon dioxide from the atmosphere, and in thinner air, there are fewer CO2 molecules available in any given volume. Plants may compensate by developing larger leaf surface areas, more efficient gas exchange mechanisms, or different metabolic pathways that allow them to function effectively in a molecular environment of high altitude. Animal adaptations to thin air at 5,000 feet begin to show more pronounced physiological modifications. Many mountain-dwelling animals have larger lung capacities, more efficient oxygen transport systems, or behavioral adaptations that help them cope with the reduced oxygen availability. Birds may show changes in their flight patterns, taking advantage of the different air density to achieve more efficient flight or developing stronger flight muscles to compensate for the reduced lift available in thin air. The cardiovascular systems of animals living permanently at 5,000 feet often show adaptations similar to those found in human populations that have lived at altitude for many generations. These might include increased red blood cell production, more efficient oxygen utilization, or enhanced cardiac output that helps maintain adequate oxygen delivery to tissues despite the reduced oxygen availability in each breath. For humans visiting 5,000 feet, the effects of thin air become noticeable but are usually not problematic for healthy individuals. You might find yourself breathing slightly more deeply or frequently during physical exertion, or notice that you become winded more easily than you would at sea level. These are normal responses to the reduced oxygen availability, and most people adapt to these moderate elevations within a few days as their bodies make physiological adjustments to the thinner air. The sensation of breathing thin air at 5,000 feet is distinctive and characteristic. The air feels lighter, less substantial as it enters your lungs. Each breath may feel less satisfying, prompting you to breathe more deeply or frequently to get the same oxygen intake you would achieve effortlessly at sea level. This isn't dangerous or problematic for most people, but it's a clear indication that you're experiencing a genuinely different atmospheric environment. As our air continues its ascent towards 6,000, 7,000, and 8,000 feet, the molecular thinning becomes increasingly pronounced. At 8,000 feet, the atmospheric pressure has dropped to about 10.9 pounds per square inch, a reduction of more than 25% from sea level conditions. The air density has decreased proportionally, creating an environment where each breath contains significantly fewer molecules than the same volume would contain in the dense air of sea level. This level of molecular thinning begins to approach the threshold where healthy individuals may experience more noticeable effects from the altitude. While 8,000 feet is still well within the range that most people can handle without difficulty, it represents a significant departure from the atmospheric conditions under which human physiology evolved. The body's response to this level of air thinning demonstrates the remarkable adaptability of biological systems, but also reveals the constraints imposed by our evolutionary heritage as sea-level creatures. The temperature at 8,000 feet, following the adiabatic lapse rate, might be 30 to 40 degrees Fahrenheit cooler than sea-level conditions. Combined with the significantly reduced air density, this creates an environment that feels dramatically different from the warm, dense air where our journey began. The molecular dance at this elevation has taken on a character that would be barely recognizable to molecules that have spent their existence in the thick air of sea level. Weather phenomena become increasingly likely and dramatic as our air reaches these higher elevations. The combination of cooling temperature, decreasing pressure, and the approaching saturation point for water vapor creates conditions where cloud formation becomes probable. The invisible water vapor that has traveled with our air throughout its journey is approaching the point where it will condense into the visible droplets that form clouds, fog, and precipitation. The boundary between clear air and cloud formation is often remarkably sharp in mountain environments, creating the dramatic cloud caps, lenticular clouds, and other orographic cloud formations that are characteristic of mountain weather. These phenomena occur when rising air reaches exactly the temperature and pressure conditions where water vapor can no longer remain invisible, suddenly transforming into billions of tiny droplets that make the air's moisture content visible for the first time since it left the ocean surface. As we observe our air at 8,000 feet, we can appreciate how far it has traveled, not just in vertical distance, but in fundamental physical transformation. The molecules that surround us are dancing to a different rhythm than they were at sea level, more widely spaced, moving more slowly due to the cooler temperature, interacting less frequently with their neighbors, creating air that has an entirely different character and behavior than the dense, warm air where the journey began. This molecular thinning represents one of the most fundamental changes that air undergoes as it crosses mountain ranges. It affects every aspect of atmospheric behavior, from the basic physics of pressure and temperature to the complex interactions that create weather patterns and support life. Understanding this molecular perspective on altitude changes helps us appreciate why mountains have such profound effects on weather, climate, and the distribution of life on our planet. In our next exploration, we'll delve deeper into the temperature changes that accompany this molecular thinning, discovering how the cooling of air with altitude follows precise physical laws that create some of the most dramatic and beautiful atmospheric phenomena we can observe in mountain environments. As our air mass continues its patient ascent through the mountain atmosphere, now climbing from 8,000 feet toward 10,000 feet and beyond, we encounter one of the most beautiful and predictable phenomena in all of atmospheric science: the steady, inexorable cooling that accompanies rising air. This cooling isn't random or chaotic, but follows mathematical relationships so precise and reliable that they've become fundamental tools for understanding weather, climate, and the behavior of our atmosphere on both local and global scales. The temperature decrease we're witnessing isn't caused by moving away from some external heat source, as you might expect if you were climbing farther from a campfire. Instead, it emerges from the fundamental physics of gases under changing pressure, a process so elegant and universal that it operates the same way whether we're observing a small parcel of air rising over a mountain or massive atmospheric currents that circle our entire planet. At 9,000 feet, our air has cooled to perhaps 45 degrees Fahrenheit, assuming it started its journey at 70 degrees at sea level. This cooling of 25 degrees represents the conversion of thermal energy into mechanical work as the air expands against the decreasing atmospheric pressure. Every molecule in our air mass participates in this process, converting some of its kinetic energy, its motion and vibration, into the work of pushing against the surrounding pressure to create the expansion that accompanies the pressure decrease. This process is called adiabatic cooling, and it occurs whenever a gas expands without exchanging heat with its surroundings. The word adiabatic comes from Greek roots meaning not passable, referring to the fact that no heat passes into or out of the air mass during this process. All the cooling comes from the internal energy of the air itself, transformed from thermal motion into mechanical work through the elegant dance of molecular physics. The rate at which dry air cools as it rises, the dry adiabatic lapse rate, is remarkably constant at about 5.4 degrees Fahrenheit per 1,000 feet of elevation, or 9.8 degrees Celsius per kilometer. This consistency isn't just a convenient approximation. It's a fundamental consequence of the physical properties of air and the universal gas laws that govern how all gases behave under changing conditions. This cooling rate is so reliable that meteorologists use it as a standard reference for predicting temperature changes with altitude. Pilots use it to understand the thermal environment they'll encounter at different flight levels. Mountain climbers and hikers use it to prepare for the temperature conditions they'll face as they ascend toward higher elevations. It represents one of those beautiful examples where complex atmospheric behavior follows simple, predictable rules. The molecular basis for this cooling lies in the relationship between temperature and molecular motion. Temperature is fundamentally a measure of the average kinetic energy of molecules, how fast they're moving, vibrating, and rotating. When air expands as pressure decreases, the molecules spread out into a larger volume, but they must do work against the surrounding pressure to achieve this expansion. This work comes directly from the kinetic energy of the molecules themselves. As they push against the surrounding pressure to expand the volume they occupy, they lose some of their motion energy, which manifests as a decrease in temperature. It's a perfectly efficient energy conversion. Thermal energy becomes mechanical energy as the air does the work of expansion against decreasing pressure. The beauty of this process is that it's completely reversible. If our air mass were to descend and encounter increasing pressure, it would be compressed, and the mechanical energy of compression would be converted back into thermal energy, warming the air at exactly the same rate it cooled during ascent. This reversibility is a hallmark of fundamental physical processes and helps explain many of the complex weather patterns we observe in mountain regions. At 10,000 feet, our air has cooled to approximately 40 degrees Fahrenheit, creating conditions that feel dramatically different from the warm sea level environment where the journey began. This cooling affects every aspect of how the air behaves and how it interacts with a mountain environment. The slower-moving molecules create air that feels crisp and sharp, with a clarity and freshness that's immediately noticeable to anyone who has experienced high-altitude conditions. The cooling air affects its capacity to hold moisture in ways that will soon become visually dramatic. Warm air can hold much more water vapor than cool air. The relationship follows an exponential curve known as the Clausius-Clapeyron relation, which described how saturation vapor pressure changes with temperature. As our air cools from 70 degrees to 40 degrees Fahrenheit, its capacity to hold moisture decreases by more than half. This dramatic reduction in moisture-holding capacity means that our air, which might have been comfortably below saturation when it was warm at sea level, is now approaching the point where it can no longer hold all its water vapor. The invisible water vapor that has traveled with our air mass throughout its journey is approaching the threshold where it will condense into visible droplets, creating the clouds and fog that are such characteristic features of mountain weather. The exact elevation where this condensation occurs depends on the initial moisture content of the air and the temperature at which it started its journey. Meteorologists call this elevation the lifting condensation level, and it marks the boundary between clear air below and clouds above. On many mountains, you can actually see this boundary as a distinct line where clouds begin to form, creating the cloud caps and lenticular formations that are so visually striking in mountain landscapes. The temperature at the lifting condensation level is called the dew point, and it represents the temperature at which the air becomes saturated with water vapor. Once our air cools to its dew point temperature, any additional cooling will cause water vapor to condense out of the air, releasing latent heat in the process and creating the visible phenomena we associate with mountain weather. As our air approaches 11,000 feet, the cooling continues relentlessly, following the same physical principles that have governed the temperature decrease throughout the ascent. But now we're approaching elevations where the temperature changes begin to create dramatic secondary effects. The air temperature might now be in the mid-30s Fahrenheit, cold enough that any water droplets that form will be at risk of freezing, creating the potential for snow rather than rain. The landscape at these elevations reflects the dramatic temperature changes that air undergoes during its mountain crossing. Vegetation becomes sparse and specialized, with plants that have adapted to the short growing seasons, intense solar radiation, and frequent freeze-thaw cycles that characterize high-altitude environments. Trees, if they exist at all, may be stunted and twisted by the harsh conditions, growing in forms that would be unrecognizable compared to their lowland relatives. The soil and rock surfaces at high elevations are subject to intense freeze-thaw cycles that gradually break down even the hardest granite into the scree and talus slopes that characterize many mountain environments. Water that seeps into rock cracks during warm afternoons freezes during cold nights, expanding and gradually splitting the rock apart in a process that operates with the patient persistence of geological time. Animal life at these elevations shows remarkable adaptations to the cold, thin air conditions. Many high-altitude animals have thick fur or feathers, efficient circulatory systems, and behavioral adaptations that help them conserve heat and maintain body temperature in an environment where the air temperature may be 40 or 50 degrees colder than at sea level. The human experience of these temperature changes is immediate and unmistakable. The cold, thin air requires different clothing, different physical preparations, and different expectations about comfort and safety. What might have been a pleasant, warm day at sea level becomes a cold, potentially dangerous environment at 11,000 feet, where hypothermia becomes a real risk if proper precautions aren't taken. The rate of temperature change with altitude creates what meteorologists call temperature gradients, zones where temperature changes rapidly over relatively short distances. These gradients drive complex atmospheric processes, creating the conditions for wind formation, cloud development, and the dramatic weather changes that can occur rapidly in mountain environments. When air masses with different temperatures encounter each other along these altitude-induced gradients, they create the potential for dynamic weather systems. Warm air tends to rise over cold air, creating convection currents that can develop into thunderstorms, while cold air can flow downhill like an invisible river, creating the mountain winds and valley breezes that are characteristic features of mountain meteorology. At 12,000 feet, our air has cooled to perhaps 30 degrees Fahrenheit, entering the realm where water exists primarily as ice rather than liquid. This transition point is crucial for understanding mountain weather, as it marks the boundary between rain and snow, between liquid clouds and ice crystal formations, between the temperate weather patterns of lower elevations and the Arctic-like conditions that prevail at high altitude. The formation of ice crystals in supercooled air droplets creates entirely different cloud structures and precipitation patterns than those that occur in warmer air. Ice crystals can grow to much larger sizes than water droplets, creating the beautiful, complex snow crystal formations that are unique to sub-freezing conditions. These ice crystals also interact with light differently than water droplets, creating the distinctive optical phenomena, halos, sundogs, and ice crystal rainbows that are characteristic of high-altitude atmospheres. The cooling air also affects the chemistry of the atmosphere in subtle but important ways. Chemical reaction rates generally slow down as temperature decreases, so the atmospheric chemistry at 12,000 feet operates at a different pace than at sea level. Pollutants may persist longer in the cold air, while natural atmospheric processes like ozone formation and destruction follow different kinetics in the frigid conditions of high altitude. The thermal stratification created by the temperature decrease with altitude also affects how air mixes vertically in mountain environments. Cold air is denser than warm air, so the cold air at high elevations tends to remain separate from the warmer air below, creating stable layers that can trap pollutants, maintain distinct weather patterns, and create the clear visibility conditions that are often observed from high mountain peaks. As our air continues toward 13 and 14,000 feet, the temperature may drop into the teens or single digits Fahrenheit, creating conditions that are genuinely Arctic despite being at latitudes that might be temperate or even subtropical at sea level. This demonstrates one of the most remarkable aspects of mountain environments: their ability to create climate zones that are completely different from the surrounding lowlands, solely through the effects of altitude on atmospheric temperature. The biological implications of these extreme temperature changes become increasingly dramatic at the highest elevations. Very few plants can survive the combination of cold temperatures, thin air, and intense solar radiation that characterizes environments above 13,000 feet. Those that do survive show extreme adaptations, growing in cushion forms to conserve heat, developing waxy surfaces to reduce water loss, or completing their entire life cycles in the brief window of favorable conditions that might last only a few weeks each year. Animal life becomes similarly specialized and rare at these extreme elevations. The few species that can survive in these conditions often show remarkable physiological adaptations. Specialized hemoglobin that can extract oxygen more efficiently from thin air, thick insulation to maintain body temperature, or behavioral patterns that allow them to take advantage of the brief periods when conditions are favorable for feeding and reproduction. For humans, these extreme elevations represent the limits of what's possible without technological assistance. The combination of cold temperatures and thin air creates conditions where survival requires careful planning, specialized equipment, and constant awareness of the risks posed by the hostile environment. Yet these same conditions create some of the most beautiful and pristine environments on Earth, where the clarity of the thin air and the dramatic temperature gradients create landscapes of extraordinary beauty and grandeur. The temperature changes we've been following represent more than just numerical decreases on a thermometer. They represent a fundamental transformation of the atmospheric environment, creating conditions that affect everything from basic physics and chemistry to complex biological and ecological processes. The cooling air tells the story of energy transformation, of work being done against pressure, of the universal physical laws that govern how matter and energy interact throughout our universe. As we prepare to explore how this cooling air responds to the decreasing pressure that accompanies its ascent, we can appreciate the elegant simplicity of the physical processes that create such complex and beautiful atmospheric phenomena. The temperature changes we've observed follow mathematical relationships that are as precise and predictable as any law of physics. Yet they create the infinitely varied and constantly changing conditions that make mountain weather so dynamic and fascinating. In our next chapter, we'll examine how the pressure changes that drive this cooling create their own cascade of effects, influencing everything from how our bodies function, to how clouds form, to how the atmosphere circulates around mountain peaks and through mountain valleys. As our air mass continues its graceful ascent beyond 14,000 feet, entering the realm where the atmosphere becomes genuinely thin and the conditions begin to challenge even the most adaptable forms of life, we encounter one of the most fundamental yet invisible forces shaping our mountain experience: the quiet, persistent decrease in atmospheric pressure that drives so many of the changes we've been observing. This pressure reduction isn't just a number that changes on barometers. It's a physical transformation that affects every aspect of how the atmosphere behaves and how living systems respond to the mountain environment. To truly understand pressure and its effects, we need to think of our atmosphere as an ocean of air, with depth measured not in fathoms of water, but in miles of gaseous atmosphere stretching from the Earth's surface to the edge of space. At sea level, we live at the bottom of this atmospheric ocean, pressed down upon by the full weight of all the air above us. This weight creates pressure in exactly the same way that water pressure increases as you dive deeper into the ocean, except that in the atmosphere, we experience maximum pressure at the bottom rather than the top. At 15,000 feet, our air exists in a realm where more than half of the atmospheric ocean lies below rather than above. The pressure here has dropped to approximately 8.3 pounds per square inch, nearly half of the 14.7 pounds per square inch that characterizes sea level conditions. This dramatic pressure reduction means that every surface at this elevation experiences significantly less force pressing upon it than the same surface would experience in the dense air of lower elevations. This pressure decrease affects the human body in ways that become increasingly noticeable and potentially significant as elevation increases. Our bodies evolved under the constant pressure of sea level atmosphere, and every physiological system is calibrated to function optimally under those conditions. The circulatory system, designed to pump blood through vessels that are supported by external atmospheric pressure, must work harder when that external pressure decreases. The respiratory system, evolved to extract oxygen from dense air, must adapt to the reality of fewer oxygen molecules in every breath. The effects of reduced pressure on human physiology begin with the basic mechanics of breathing. At sea level, the pressure difference between the inside of your lungs and the outside atmosphere creates a natural driving force that helps move air in and out of your respiratory system. At 15,000 feet, this pressure difference is reduced, making it slightly more difficult for your lungs to expand fully and creating the sensation that each breath is less satisfying than it would be at lower elevations. More significantly, the reduced pressure affects how efficiently oxygen can be transferred from your lungs into your bloodstream. This transfer depends partly on pressure gradients, and when atmospheric pressure decreases, the driving force for oxygen absorption is reduced accordingly. Your body compensates by breathing more frequently and more deeply, but these adaptations require energy and can lead to fatigue during physical exertion. The reduced pressure also affects how gases dissolved in body fluids behave. Under normal sea level pressure, gases like nitrogen dissolve readily in blood and other body fluids and remain in solution without causing problems. But as pressure decreases dramatically, dissolved gases can begin to form bubbles, similar to what happens when you open a carbonated beverage. While this effect doesn't become dangerous until much higher altitudes, it represents another way that changing pressure affects biological systems. Plants at 15,000 feet show remarkable adaptations to the reduced pressure environment. The lower atmospheric pressure affects how easily water can evaporate from leaf surfaces, potentially leading to increased water loss through transpiration. Many high-altitude plants have developed smaller, thicker leaves with waxy surfaces that help reduce this water loss. They may also have modified stomata, the tiny pores through which plants exchange gases with the atmosphere, that can open and close more efficiently in a low-pressure environment. The reduced pressure also affects how plants can transport water from their roots to their leaves. Water transport in plants depends partly on pressure differences, and the lower external pressure at high altitude can actually make it easier for plants to move water upward against gravity. However, this advantage is often offset by the increased evaporation rates and the challenges of obtaining sufficient carbon dioxide for photosynthesis from the thin atmosphere. The pressure changes create fascinating effects on the physical properties of materials at high altitude. Water boils at lower temperatures when pressure is reduced, so at 15,000 feet, water boils at about 185 degrees Fahrenheit instead of the 212 degrees Fahrenheit that characterizes sea level conditions. This seemingly simple change has practical implications for cooking, food safety, and any industrial processes that depend on precise temperature control. The lower boiling point of water also affects weather processes in subtle but important ways. Cloud droplets and ice crystals form and evaporate differently under reduced pressure conditions, creating cloud structures and precipitation patterns that are unique to high-altitude environments. The delicate balance between evaporation and condensation that determines cloud behavior is shifted by the pressure changes, contributing to the distinctive weather patterns that characterize mountain environments. As our air approaches 16,000 feet, the pressure drops to about 7.5 pounds per square inch, roughly half of sea level pressure. At this elevation, we're truly in the realm of high-altitude physiology, where the human body's response to pressure and oxygen changes becomes increasingly pronounced. Healthy individuals may begin to experience the early symptoms of altitude sickness, headaches, fatigue, nausea, or difficulty sleeping, as their bodies struggle to adapt to the dramatically different atmospheric conditions. The reduced pressure at these elevations affects the behavior of gases in ways that create unique atmospheric phenomena. The lower pressure allows air to expand more readily, creating conditions where small temperature differences can drive vigorous convection currents. This enhanced convection can lead to rapid cloud formation and dramatic weather changes that seem to appear from nowhere, contributing to the reputation of high mountains for unpredictable and rapidly changing conditions. The expansion of air due to reduced pressure also affects how sound travels through the mountain atmosphere. Sound waves propagate through air by creating alternating compressions and rarefactions, regions where air molecules are pushed closer together alternating with regions where they're spread farther apart. In the low-pressure environment of high altitude, there are fewer molecules available to participate in these pressure waves, and the reduced baseline pressure affects how efficiently sound energy can be transmitted. The acoustic environment at 16,000 feet has a distinctive character that experienced mountaineers learn to recognize. Sounds may seem clearer and more distinct because there's less molecular interference, but they may also seem to fade more quickly with distance. The thin air carries voices differently, and the acoustic landmarks that help with navigation in dense air. The sound of running water, the rustle of vegetation, the echo patterns from rock faces, all behave differently in the low-pressure environment of high altitude. Weather instruments respond dramatically to the pressure changes at these elevations. Barometers, which measure atmospheric pressure directly, show readings that would indicate severe storms if they occurred at sea level. An altimeter, which measures elevation by detecting pressure changes, becomes an essential tool for navigation in an environment where pressure varies dramatically over relatively short vertical distances. The pressure changes also affect how aircraft operate in mountain environments. Airplane engines, designed to mix fuel with air in precise ratios, must compensate for the reduced air density. Helicopter rotors, which generate lift by pushing air downward, become less efficient in thin air and may be unable to operate at all above certain elevations. Even simple devices like cooking stoves may operate differently or less efficiently in the low-pressure environment of high altitude. As our air continues towards 17 and 18,000 feet, the pressure decreases to levels that represent genuine challenges for unacclimatized humans. At 18,000 feet, the pressure is approximately 6.8 pounds per square inch, less than half of sea level values. The partial pressure of oxygen, which determines how much oxygen is available for biological processes, has decreased proportionally, creating conditions where even basic biological functions become significantly more difficult. The reduced pressure affects the formation and behavior of clouds in ways that create the spectacular mountain weather phenomena that are visible from great distances. Lenticular clouds, those smooth, lens-shaped formations that often cap mountain peaks, form when moist air is forced to rise rapidly over mountain ridges and then descends on the lee side. The pressure changes associated with this forced vertical motion create alternating zones of condensation and evaporation that shape the distinctive, smooth appearance of these clouds. Wave clouds, rotor clouds, and banner clouds all owe their existence to the complex pressure patterns that develop when air flows over and around mountain obstacles. These pressure variations create three-dimensional patterns of rising and sinking air that can extend for many miles downwind of the mountain peaks, creating visible cloud formations that reveal the invisible architecture of atmospheric pressure variations. The pressure reduction at extreme altitudes also affects the behavior of the jet stream and other high-altitude atmospheric phenomena. Commercial aircraft flying at cruising altitudes of 30 to 40,000 feet operate in pressure environments that are even more extreme than the highest mountain peaks, where the pressure may be only 1/4 or less of sea level values. The interaction between these extreme pressure environments and mountain topography can create complex wind patterns that affect aviation, weather prediction, and atmospheric circulation on regional and global scales. At 19,000 feet and above, our air exists in pressure conditions that are genuinely hostile to most forms of life. The pressure here might be 6 pounds per square inch or less, roughly 1/3 of sea level pressure. Few plants can survive these conditions, and animals that venture to these elevations do so only briefly and with significant physiological stress. Humans require supplemental oxygen or extensive acclimatization to function at these elevations, and even then, the margin for error becomes very small. The reduced pressure affects basic biological processes in ways that become increasingly significant as elevation increases. Cell membranes, evolved to function under standard atmospheric pressure, may behave differently when external pressure is dramatically reduced. Enzyme reactions that depend on pressure-sensitive conformational changes in protein molecules may operate less efficiently. Even the simple process of cellular respiration becomes more challenging when the pressure gradients that drive oxygen transport are significantly reduced. The pressure environment at extreme altitude also affects the behavior of water in biological systems. Water vapor pressure increases as external pressure decreases, making it easier for organisms to lose water through respiration and skin surfaces. This enhanced water loss can lead to rapid dehydration, especially in the dry air that typically characterizes high-altitude environments. The interaction between reduced pressure and cold temperatures creates particularly challenging conditions for biological systems. Cold air holds less moisture than warm air, and the low pressure enhances evaporation rates, creating extremely dry conditions that can quickly lead to dehydration of exposed tissues. The combination of pressure and temperature effects makes extreme altitude environments particularly hostile to life forms that aren't specifically adapted to these conditions. Yet despite these challenges, the pressure environment of extreme altitude also creates conditions of extraordinary beauty and clarity. The thin air at high elevation provides unparalleled visibility, allowing views that can extend for hundreds of miles on clear days. The reduced atmospheric interference creates conditions where distant objects appear with remarkable clarity and detail, and the curvature of the Earth may become visible from the highest peaks. The reduced pressure also affects how light behaves in the atmosphere, creating optical phenomena that are unique to high-altitude environments. The aurora-like effects of sunlight interacting with ice crystals in the thin air, the intense blue color of the sky in low-pressure conditions, and the brilliant clarity of starlight in the rarefied atmosphere all result from the unique optical properties of air under dramatically reduced pressure. As we observe our air at these extreme elevations, we can appreciate how this simple reduction in atmospheric pressure creates a cascade of effects that transform every aspect of the mountain environment. From the basic physics of gas behavior to the complex physiological adaptations of living systems, the pressure changes that accompany altitude create conditions that are as fascinating as they are challenging. The quiet release of pressure that occurs as air rises over mountains represents one of the most fundamental atmospheric processes, yet it creates effects that touch every aspect of mountain environments. Understanding these pressure effects helps us appreciate why mountains have such profound impacts on weather, climate, and the distribution of life on our planet, and why the thin air of high altitude creates conditions that are both beautiful and demanding in equal measure. In our next exploration, we'll discover how this reduced pressure combines with the cooling temperatures we've already explored to create one of the most critical challenges facing life at altitude: the gradual retreat of oxygen that makes the thin air of high mountains both literally and figuratively breathtaking. As our air mass continues its remarkable journey toward the highest elevations where only the most specialized forms of life can survive, we encounter what is perhaps the most profound and life-altering aspect of mountain atmospheres: the gradual but inexorable decrease in available oxygen that occurs as air density diminishes with altitude. This isn't simply a matter of there being less air to breathe, though that's certainly part of the story. Rather, it's a complex interplay of physics, chemistry, and biology that reveals just how precisely tuned life on Earth is to the specific atmospheric conditions that exist at sea level. At 20,000 feet, our traveling air mass exists in an environment where oxygen, while still comprising the same percentage of the atmosphere as it does at sea level, is present in such reduced concentrations that every breath contains only about half the oxygen molecules that would be available in the same volume of air at sea level. This reduction follows directly from the decreased air density we've been observing throughout our ascent, but its biological implications are far more dramatic than the simple mathematics might suggest. To understand why oxygen becomes such a critical factor at high altitude, we need to appreciate that life on Earth evolved under very specific atmospheric conditions. For billions of years, complex life forms have developed respiratory and circulatory systems that are precisely calibrated to extract oxygen from air that contains approximately 21% oxygen at sea level pressure. Every aspect of how animals breathe, how blood transports oxygen, and how cells consume oxygen for energy production is optimized for these particular conditions. The oxygen molecules in our high-altitude air are still oxygen molecules, chemically identical to those at sea level, with the same ability to support combustion and cellular respiration. What has changed is their concentration, their partial pressure, and the driving forces that determine how easily they can be extracted from the air and transported to the tissues that need them. At 20,000 feet, the partial pressure of oxygen, the portion of total atmospheric pressure that's contributed by oxygen molecules, has dropped to about 6.3 pounds per square inch, compared to 3.1 pounds per square inch at sea level. This reduction in oxygen partial pressure affects the fundamental physics of how oxygen moves from the atmosphere into biological systems. Oxygen transport depends on pressure gradients. Oxygen moves from regions of higher pressure to regions of lower pressure, just like any other gas. When the atmospheric pressure of oxygen decreases dramatically, the driving force for oxygen uptake by the lungs is correspondingly reduced, making it more difficult for the respiratory system to maintain adequate oxygen levels in the blood. The human body's response to this oxygen reduction begins with immediate, short-term adjustments that you can feel happening in real time. Your breathing rate increases as your respiratory system attempts to compensate for the lower oxygen concentration by moving more air through your lungs. Your heart rate may increase as your circulatory system works harder to transport the available oxygen to your tissues. You may feel lightheaded or dizzy as your brain, which consumes about 20% of your body's oxygen supply, experiences the effects of reduced oxygen availability. These immediate responses represent your body's emergency measures for dealing with oxygen scarcity, but they're not sustainable long-term solutions. Breathing harder and faster requires energy, and your heart working harder puts additional strain on your cardiovascular system. If you remain at high altitude for extended periods, your body begins to make more fundamental physiological adaptations to the low oxygen environment. Over days to weeks at high altitude, your body begins producing more red blood cells, the specialized cells that transport oxygen from your lungs to your tissues. This process, called polycythemia, increases the oxygen-carrying capacity of your blood, allowing each heartbeat to deliver more oxygen even when the concentration of oxygen in each breath is reduced. Your existing red blood cells also begin producing more hemoglobin, the protein that actually binds to oxygen molecules and releases them where they're needed. These adaptations take time to develop and represent significant metabolic investments for your body. Producing additional red blood cells requires energy, nutrients, and raw materials that must be diverted from other biological processes. The increased concentration of red blood cells also makes your blood thicker and more viscous, requiring your heart to work harder to pump it through your circulatory system. At 22,000 feet, the oxygen situation becomes even more challenging. Here, the partial pressure of oxygen has dropped to levels that would be considered dangerous or even life-threatening for unacclimatized individuals. The air contains only about 42% of the oxygen available at sea level, creating conditions where even basic biological functions become significantly more difficult to maintain. Plants at these extreme elevations face their own unique challenges related to oxygen availability. While plants produce oxygen through photosynthesis during daylight hours, they also consume oxygen through respiration, just like animals. At night, when photosynthesis stops, but respiration continues, plants at extreme altitude must extract the oxygen they need from the same thin air that challenges animal life. The reduced oxygen availability affects plant metabolism in complex ways. Cellular respiration, the process by which plants convert stored sugars into usable energy, requires oxygen to operate efficiently. When oxygen is scarce, plants may be forced to rely more heavily on less efficient anaerobic metabolic pathways, reducing their overall energy production and limiting their ability to grow and reproduce. High-altitude plants have evolved remarkable adaptations to cope with these oxygen limitations. Many have developed more efficient respiratory systems at the cellular level, with specialized organelles that can extract maximum energy from limited oxygen supplies. Others have evolved metabolic pathways that require less oxygen or can operate efficiently under low oxygen conditions. The sparse vegetation that manages to survive at 22,000 feet and above often grows in forms that seem almost alien compared to lowland plants. Cushion plants, which grow in tight, compact mounds close to the ground, represent one common adaptation strategy. This growth form helps conserve heat and moisture while minimizing the plant's oxygen requirements by reducing the amount of metabolically active tissue that must be maintained. Animal life at these extreme elevations is limited to a few highly specialized species that have evolved extraordinary adaptations to the low-oxygen environment. High-altitude birds like the bar-headed goose, which migrates over the Himalayas at elevations exceeding 28,000 feet, have hemoglobin with unusually high oxygen affinity, allowing them to extract oxygen from air so thin that it would quickly incapacitate most other animals. These birds also have enlarged hearts and lungs relative to their body size, more efficient respiratory systems that can extract more oxygen from each breath, and circulatory systems that can transport oxygen more efficiently to their flight muscles. During their remarkable migrations, they essentially operate as biological aircraft specifically adapted to function in the oxygen-poor environment of extreme altitude. Mammals that live permanently at high altitude show similarly dramatic adaptations. The vicuña, a relative of the llama that lives in the Andes at elevations above 14,000 feet, has blood with an unusually high concentration of red blood cells and hemoglobin that's specially adapted to function efficiently in low oxygen conditions. Their hearts are proportionally larger than those of lowland mammals, and their circulatory systems are optimized for oxygen transport under challenging conditions. Human populations that have lived at high altitude for many generations show genetic adaptations that help them cope with chronic oxygen limitation. Tibetans, Andean peoples, and other high-altitude populations have evolved physiological modifications that allow them to maintain normal activity levels in conditions that would severely impair lowland peoples. These adaptations include more efficient oxygen utilization at the cellular level, modified hemoglobin that can carry oxygen more effectively in low-pressure conditions, and circulatory systems that are optimized for high-altitude environments. As our air approaches 24,000 feet, we enter the realm that mountaineers call the death zone, elevations where the oxygen concentration is so low that human life cannot be sustained indefinitely, even with perfect acclimatization. At these elevations, the partial pressure of oxygen is less than 1/3 of sea level values, creating conditions where cellular respiration becomes increasingly difficult to maintain. The term death zone isn't meant to be dramatic or frightening. It's simply a recognition of the biological reality that human physiology has limits, and that above certain elevations, the atmosphere can no longer support human life for extended periods. Even the most highly acclimatized individuals can only survive at these elevations for limited periods before their bodies begin to experience irreversible damage from chronic oxygen deprivation. The effects of severe oxygen limitation at these extreme altitudes affect every system in the human body. Brain function becomes impaired as neurons struggle to maintain normal activity levels without adequate oxygen. Decision-making abilities deteriorate, reaction times slow, and the risk of altitude-related cerebral edema, a potentially fatal condition where fluid accumulates in the brain, increases significantly. The cardiovascular system is pushed to its absolute limits, trying to maintain oxygen delivery to vital organs. Heart rates may remain elevated continuously, blood pressure changes can occur, and the risk of altitude-related pulmonary edema, fluid accumulation in the lungs that interferes with oxygen uptake, becomes a serious concern. The body's attempts to adapt to extreme oxygen limitation can sometimes create additional problems that compound the original challenge. Sleep becomes increasingly difficult at extreme altitude, partly due to the oxygen limitation and partly due to the physiological stress of trying to maintain normal body functions under such challenging conditions. The combination of poor sleep, physical stress, and chronic oxygen deprivation creates a cycle that makes it increasingly difficult for the body to maintain the adaptations necessary for high-altitude survival. Yet despite these challenges, a few remarkable individuals have demonstrated that humans can survive and even function at the most extreme altitudes on Earth. Mountain climbers have reached the summit of Mount Everest at 29,032 feet without supplemental oxygen, demonstrating the extraordinary adaptability of the human body when pushed to its absolute limits. These achievements require not only exceptional physical conditioning and acclimatization, but also genetic advantages and an almost supernatural ability to function under conditions that would quickly incapacitate most people. The oxygen limitation at extreme altitude also affects the behavior of fire and combustion in ways that can be surprising and potentially dangerous. Fire requires oxygen to burn, and in the thin air of high altitude, flames burn differently than they do at sea level. Cooking stoves may operate less efficiently, requiring more fuel to produce the same amount of heat. Fires may be more difficult to start and maintain, and the reduced oxygen availability can affect how efficiently fuel burns. These combustion effects have practical implications for anyone spending time at high altitude. Heating systems, cooking equipment, and emergency signaling devices all operate differently in low-oxygen environments. Understanding these effects is crucial for safety and survival in extreme altitude environments, where equipment failure or inefficient operation can quickly become life-threatening situations. The reduced oxygen availability also affects how the human body processes and metabolizes various substances. Alcohol tolerance decreases significantly at high altitude, partly due to the oxygen limitation and partly due to other physiological changes that occur with altitude exposure. Medications may be processed differently by the liver and kidneys, potentially altering their effectiveness or side effects. Even caffeine, which many people rely on for mental alertness, may have different effects in the low-oxygen environment of high altitude. As our air reaches 26,000 feet and beyond, we encounter oxygen concentrations that represent the absolute limits of what's possible for air-breathing life on Earth. At these elevations, the partial pressure of oxygen is so low that even breathing pure oxygen through a mask might not provide adequate oxygen delivery to maintain normal physiological function. The few aircraft that operate at these extreme altitudes require pressurized cabins that maintain artificial atmospheric conditions for their occupants. Commercial airliners that cruise at 30 to 40,000 feet create artificial environments inside their cabins that simulate conditions at about 8,000 feet elevation, still thin enough that passengers might notice the effects, but dense enough to maintain safe and comfortable conditions for extended periods. The study of oxygen limitation at extreme altitude has provided crucial insights into human physiology and has contributed to medical understanding of respiratory and circulatory diseases that affect oxygen transport and utilization. The adaptations that allow some people to function at extreme altitude have informed treatments for conditions like chronic obstructive pulmonary disease, heart failure, and other conditions that involve compromised oxygen delivery to tissues. Research conducted at high-altitude research stations has also contributed to our understanding of space physiology and the challenges that astronauts face in the low-pressure environments of spacecraft and space stations. The parallels between high-altitude and space environments have made mountain research an important component of preparing humans for space exploration and long-duration space missions. As we observe our air at these extreme elevations, we can appreciate the profound challenges that oxygen limitation creates for life on Earth. The gradual retreat of oxygen with altitude represents one of the most fundamental constraints on where and how life can exist on our planet. Yet it also demonstrates the remarkable adaptability of living systems and the extraordinary lengths to which evolution can go to allow life to thrive in even the most challenging environments. The oxygen story in mountain atmospheres reminds us how precisely calibrated life on Earth is to the specific atmospheric conditions that exist at sea level, while also revealing the remarkable resilience and adaptability of biological systems when faced with environmental challenges. In our next exploration, we'll discover how the reduced oxygen combines with other atmospheric changes to affect one of the most visible and dynamic aspects of mountain weather: the behavior of moisture and the formation of the clouds that crown mountain peaks with beauty and drama. As our air mass continues its magnificent ascent through the increasingly rarefied atmosphere above 20,000 feet, we encounter one of the most visually spectacular and scientifically fascinating aspects of mountain meteorology: the transformation of invisible water vapor into the countless forms of visible moisture that create the clouds, fog, snow, and precipitation phenomena that make mountain weather so dynamic and beautiful. This transformation represents a fundamental change of state, where water molecules that have been traveling invisibly with our air throughout its journey suddenly become visible participants in atmospheric drama. The story of moisture in mountain atmospheres begins with understanding that our air has been carrying water with it throughout its entire journey from sea level. This water exists as individual water vapor molecules mixed invisibly among the nitrogen, oxygen, and other gases that make up our atmosphere. At sea level, where our air began its journey, the warm temperatures allowed it to hold substantial amounts of this invisible moisture, perhaps enough water vapor that, if it could all be condensed at once, would create a thin layer of liquid water covering every surface. But as our air has risen and cooled according to the adiabatic lapse rate we explored earlier, its capacity to hold this moisture has decreased dramatically. Warm air can hold exponentially more water vapor than cold air. This relationship follows what scientists call the Clausius-Clapeyron relation, which describes how the saturation vapor pressure of water changes with temperature. As our air has cooled from perhaps 70 degrees Fahrenheit at sea level to below freezing at high altitude, its moisture-holding capacity has decreased by more than 80%. At 22,000 feet, where temperatures may be well below 0 Fahrenheit and the air pressure has dropped to less than half of sea level values, our air is approaching or may have already reached its saturation point, the temperature and pressure conditions where it can no longer hold all its water vapor in invisible gaseous form. When air becomes saturated, any additional cooling or any slight increase in moisture content will cause water vapor to begin condensing into visible droplets or, at these cold temperatures, depositing directly into ice crystals. The process of condensation and deposition represents one of the most beautiful examples of phase transitions in nature. Individual water vapor molecules, which have been moving freely through the air as independent gas particles, suddenly begin to collect together, forming tiny droplets or crystals that are large enough to scatter light and become visible. This transition doesn't happen all at once throughout the air mass, but rather begins at specific points called condensation nuclei, tiny particles of dust, salt, pollen, or other microscopic material that provide surfaces where water molecules can begin to collect. In the pristine air of high mountain environments, condensation nuclei may be scarce, which can lead to supercooling, conditions where water vapor remains in gaseous form even though the temperature and pressure conditions would normally favor condensation. When condensation finally does occur in supercooled air, it can happen very rapidly, creating the sudden appearance of clouds or fog that seems to materialize out of clear air in a matter of minutes. The formation of clouds at high altitude creates some of the most distinctive and beautiful weather phenomena associated with mountain environments. Lenticular clouds, those smooth, lens-shaped formations that often hover near mountain peaks, form when moist air is forced to rise rapidly over mountain ridges and then descends on the lee side. As the air rises, it cools and reaches saturation, forming clouds. As it descends and warms on the other side of the mountain, the moisture evaporates back into invisible vapor, creating stationary cloud formations that can persist for hours while air continuously flows through them. These lenticular clouds reveal the invisible architecture of airflow over mountains, making visible the standing waves and turbulence that develop when moving air encounters solid topography. They're like flags showing the direction and strength of high-altitude winds, and their smooth, almost artificial appearance has led to numerous UFO reports from observers who aren't familiar with mountain meteorology. Banner clouds represent another spectacular example of orographic cloud formation. These streamer-like clouds form in the lee of mountain peaks when moist air flows around rather than over the mountain, creating areas of reduced pressure and enhanced cooling on the downwind side. The Matterhorn's famous banner cloud, which often extends like a flag from the mountain summit, forms through exactly this process, creating one of the most photographed cloud formations in the world. As our air encounters the complex topography of high mountain peaks, the moisture it carries begins to behave in increasingly dramatic ways. Wave clouds form when air flowing over mountains sets up oscillating patterns downwind, creating alternating zones of rising and sinking air that produce parallel bands of clouds separated by clear air. These wave patterns can extend for dozens of miles downwind of mountain ranges, creating visible evidence of how topography influences atmospheric circulation far from the mountains themselves. Rotor clouds form in the turbulent air that develops in the lee of mountain ridges, where strong downslope winds create rotating cylinders of air. These clouds often have a ragged, constantly changing appearance that reflects the chaotic air motions within them. While beautiful to observe from a distance, rotor clouds indicate areas of severe turbulence that can be extremely hazardous for aircraft. The behavior of moisture at extreme altitude is also affected by the very low air pressure that characterizes these elevations. At reduced pressure, water can exist in states that would be impossible at sea level pressure. Supercooled water droplets, liquid water that remains unfrozen at temperatures well below the normal freezing point, can persist at high altitude because the reduced pressure lowers the energy barrier for maintaining the liquid state. These supercooled droplets create hazardous conditions for aircraft, as they can freeze instantly upon contact with any surface, creating dangerous ice accumulations on wings and control surfaces. The same process can create beautiful but treacherous rime ice formations on exposed surfaces at high altitude, where supercooled fog droplets freeze instantly upon contact with rocks, vegetation, or equipment. The formation of ice crystals in the thin air of high altitude creates optical phenomena that are unique to these environments. Sundogs, or parhelia, form when sunlight is refracted by ice crystals in thin, high-altitude clouds, creating bright spots that appear on either side of the sun. Halos form when light passes through ice crystals oriented in specific ways, creating circular rings of light around the sun or moon. These optical effects are much more common at high altitude, where the cold temperatures and thin air favor the formation of the precise ice crystal structures that create these beautiful displays. The snow that forms at high altitude often has characteristics that are quite different from snow that forms at lower elevations. In the extremely cold, dry air of high mountains, snow crystals can maintain their delicate, intricate structures for much longer periods than they would in the warmer, moister air of lower elevations. This creates snow conditions that are prized by skiers and mountaineers. Powder snow that remains light and fluffy for extended periods because the individual crystals don't bond together or deteriorate as quickly as they would under different atmospheric conditions. The process of sublimation, the direct transition from ice to water vapor without passing through the liquid phase, becomes increasingly important at high altitude. In the dry air and intense solar radiation of high mountain environments, snow and ice can sublimate rapidly, returning moisture directly to the atmosphere without melting. This process can create conditions where snow seems to disappear without any obvious melting, and it contributes to the extremely dry air conditions that characterize many high-altitude environments. Wind patterns at high altitude affect moisture behavior in complex ways. The jet stream, which often flows at elevations between 25 and 40,000 feet, can transport moisture rapidly across continents, creating high-altitude cloud formations that influence weather patterns far from their origins. These high-altitude moisture transports can bring water vapor from oceanic regions to continental interiors, where it may eventually precipitate as snow on high mountain peaks. Orographic lifting, the forced ascent of air masses as they encounter mountain ranges, creates some of the most reliable precipitation patterns on Earth. Mountain ranges like the Sierra Nevada, the Cascades, and the Rocky Mountains create barriers that force moist air from the Pacific Ocean to rise and cool, dropping much of their moisture as rain and snow on the windward slopes. This process creates the distinct climate patterns that characterize many mountain regions, with wet conditions on the windward side and dry conditions in the rain shadow on the lee side. The amount of precipitation that falls at high altitude can be enormous, with some mountain locations receiving several hundred inches of snow annually. This precipitation represents moisture that began its journey over distant oceans, traveled thousands of miles through the atmosphere, and finally condensed out when it encountered the cooling effects of orographic lifting. The snow and ice that accumulate at high altitude serve as natural reservoirs, storing water that will gradually be released through melting and runoff during warmer seasons. Glaciers represent the ultimate expression of moisture accumulation in high mountain environments. These massive ice formations develop when more snow falls during winter than melts during summer, allowing ice to accumulate over many years or decades. The glacial ice preserves a record of past atmospheric conditions, with air bubbles trapped in the ice, providing samples of ancient atmospheres that scientists can study to understand how climate and atmospheric composition have changed over time. The behavior of moisture in high-altitude environments also affects the formation of unique weather phenomena like virga, precipitation that evaporates before reaching the ground. In the dry air of high altitude, rain or snow may begin to fall from clouds, but completely evaporate during its descent through the thin, dry air below. This creates the ethereal sight of precipitation streamers hanging from clouds without reaching the surface, like curtains of moisture suspended in the sky. Cloud-to-ground lightning becomes less common at very high altitudes, partly due to the reduced air density and partly due to the different charge distributions that develop in thin air environments. However, other electrical phenomena may become more prominent. St. Elmo's fire, the eerie glow that can appear on pointed objects during electrical storms, may be more likely to occur in the thin air of high altitude, where electrical fields can build up to higher intensities before breakdown occurs. The diurnal cycle of moisture behavior becomes particularly pronounced in high mountain environments. During the day, intense solar radiation at high altitude can cause rapid heating and convection, leading to the formation of afternoon thunderstorms even when mornings were clear. At night, rapid cooling can lead to fog formation and frost deposition as the moisture capacity of the cold air drops below the actual moisture content. The interaction between moisture and the intense solar radiation of high altitude creates unique challenges for both natural systems and human activities. The combination of high moisture content in some forms, like fog or snow, with intense ultraviolet radiation can create conditions where sunburn and snow blindness become serious risks. The high reflectivity of snow and ice can create intense glare that makes protective eyewear essential for safety. Fog behavior at high altitude can be dramatically different from fog at sea level. Valley fog may form when cold air drains down mountain slopes and collects in valleys, creating temperature inversions where cold, moist air is trapped beneath warmer, drier air above. These inversions can persist for days in some mountain environments, creating conditions where valleys remain shrouded in fog while peaks emerge into brilliant sunshine above. The freeze-thaw cycles that occur when moisture transitions between liquid and solid states become dominant processes in shaping high-altitude landscapes. Water that seeps into rock cracks during warm periods freezes during cold periods, expanding and gradually breaking apart even the hardest granite. This frost weathering process operates continuously in high mountain environments, gradually reducing massive rock formations to the scree slopes and boulder fields that characterize many alpine landscapes. As we observe the behavior of moisture in our high-altitude air mass, we can appreciate how this most familiar of substances, water, takes on entirely new characteristics and behaviors in the extreme conditions of mountain environments. The invisible water vapor that began its journey over distant oceans has become a visible and dynamic participant in atmospheric processes that create some of the most beautiful and dramatic weather phenomena on Earth. The transformation of moisture from invisible gas to visible clouds, from liquid droplets to ice crystals, from falling precipitation to accumulated snow and ice, represents one of the most fundamental and important cycles in Earth's climate system. Understanding these transformations helps us appreciate how mountains influence weather and climate on both local and global scales, and how the simple act of air rising over topography can create the complex and beautiful atmospheric phenomena that make mountain environments so captivating and dynamic. In our next exploration, we'll discover how the transformed air that has experienced all these changes in pressure, temperature, oxygen content, and moisture behavior begins to flow in new patterns shaped by the solid topography of the mountains themselves, creating the winds and air currents that give each mountain range its own distinctive atmospheric personality. As our air mass encounters the increasingly complex topography of high mountain terrain, having been transformed by its journey through changing pressure, temperature, and moisture conditions, it begins to flow in patterns that are entirely different from the broad, smooth currents that characterize air movement over flat terrain. The solid rock of mountain ridges, peaks, and valleys doesn't just passively deflect the moving air. It teaches the atmosphere new ways to flow, creating wind patterns that are as complex and varied as the topography itself. The interaction between moving air and solid mountain terrain creates what meteorologists call orographic effects, changes in wind patterns that are caused specifically by the presence of mountains and hills. These effects transform our traveling air mass from a participant in large-scale atmospheric circulation into a player in the intricate, localized wind systems that give each mountain range its own distinctive atmospheric character. At the most basic level, when moving air encounters a mountain ridge, it faces a choice that's determined by the physics of fluid flow around obstacles. The air can flow over the mountain, around the mountain, or through any available passes and valleys that provide pathways of lower resistance. The specific choice depends on factors like the speed of the wind, the height and steepness of the topography, and the stability of the atmospheric conditions. When our air chooses to flow over a mountain ridge, it experiences what's called orographic lifting, the forced ascent that we've been following throughout our journey. But this lifting isn't uniform or simple. As air flows over complex topography, it accelerates on the windward slopes, reaching maximum speeds near the ridge crest, and then often experiences dramatic changes in speed and direction as it flows down the leeward slopes. This acceleration over ridges follows the principle of conservation of mass and fluid flow. As air is forced through the narrower space between the ground and higher atmospheric layers, it must speed up to maintain the same mass flow rate. It's similar to what happens when you partially cover the end of a garden hose with your thumb. The water speeds up as it's forced through the smaller opening. In mountain environments, this acceleration can create winds that are dramatically stronger near ridge crests than they are just a few hundred feet lower on the slopes. The downslope flow on the leeward side of mountain ridges creates some of the most distinctive and powerful wind phenomena in mountain meteorology. Chinook winds in the Rocky Mountains, Fein winds in the Alps, and Santa Ana winds in Southern California all represent examples of air that has been heated and dried as it flows down the leeward slopes of mountain ranges. These winds can raise temperatures by 30 or 40 degrees Fahrenheit in a matter of hours, melting snow rapidly and creating fire weather conditions even in the middle of winter. The heating that creates these warm, downslope winds occurs through the same adiabatic processes we've been exploring, but operating in reverse. As air descends from high altitude and encounters increasing atmospheric pressure, it's compressed and heated at the same rate it was cooled during ascent. However, if the air lost moisture through precipitation during its passage over the mountain, it will be drier on the descent than it was on the ascent, and this drying creates additional warming effects that can make downslope winds dramatically warmer than the original air mass. When air flows around mountains rather than over them, it creates entirely different but equally fascinating wind patterns. Mountain ranges act like giant obstacles in the atmospheric flow, creating areas of acceleration on the flanks where air is forced to speed up as it flows around the barrier. These acceleration zones can create Venturi effects, where wind speeds increase dramatically in the gaps between peaks or in the constricted spaces where air is forced to flow around complex topography. The Cascade Range in the Pacific Northwest provides excellent examples of both over-mountain and around-mountain flow patterns. During winter storms, moist air from the Pacific Ocean may flow directly over the range, creating heavy precipitation on the western slopes and dramatically different conditions on the eastern slopes. During other conditions, air may flow around the northern and southern ends of the range, creating complex convergence patterns where air streams that have taken different paths around the mountains meet and interact. Valley winds represent another class of mountain wind phenomena that develop through the interaction between topography and differential heating. During the day, solar heating warms the slopes of mountain valleys more rapidly than it warms the valley floors, creating temperature differences that drive local circulation patterns. Warm air rises along the heated slopes, creating up-valley winds that flow from lower elevations toward higher elevations, exactly opposite to what gravity alone would suggest. At night, the process reverses as the slopes cool more rapidly than the valley floors through radiative cooling to the clear mountain sky. Cold air becomes denser and flows downhill, creating down-valley winds that can persist through the night and into the early morning hours. These diurnal wind patterns are so reliable in many mountain regions that local residents plan activities around them, knowing that afternoons will bring up-valley winds while mornings will be characterized by down-valley flows. The thermal structure of mountain valleys creates complex layering effects that can trap air masses and create distinct microenvironments. Cold air drainage can create temperature inversions in valleys, where the coldest air collects at the bottom while warmer air exists at higher elevations. These inversions can persist for days during stable weather conditions, creating fog and frost in the valleys while higher elevations enjoy clear, warm conditions. Gap winds represent some of the most dramatic examples of topographically influenced airflow. When pressure differences exist across mountain ranges, air can be forced through narrow passes at extremely high velocities. The Columbia River Gorge, which cuts through the Cascade Range, is famous for gap winds that can exceed 100 miles per hour as air is funneled through this natural corridor between high-pressure systems east of the mountains and low-pressure systems to the west. These gap winds can persist for days during certain weather patterns, creating conditions that are simultaneously challenging and exhilarating. The same geographic features that create hazardous conditions for aviation and surface transportation also create world-class windsurfing and kiteboarding conditions, demonstrating how mountain wind phenomena can be both dangerous and beneficial depending on the context. Mountain wave phenomena create some of the most complex and fascinating wind patterns in mountain meteorology. When stable air flows over mountain ridges at the right speed and atmospheric conditions, it can set up oscillating wave patterns that extend for many miles downwind of the mountains. These waves are invisible to the naked eye, but can be detected by specialized instruments and are made visible by the wave clouds that often form at the wave crests. Mountain waves can extend from the surface up to the stratosphere, creating standing wave patterns that remain stationary relative to the ground while air flows continuously through them. These waves can create extremely strong updrafts and downdrafts that can exceed 3,000 feet per minute. Rates of vertical air motion that are strong enough to carry gliders to extreme altitudes or create severe turbulence for aircraft. The rotors that form beneath mountain waves create some of the most turbulent air conditions found anywhere in the atmosphere. These rotating cylinders of air can extend for several miles downwind of mountain ridges, creating conditions where wind direction and speed can change dramatically over very short distances. The turbulence in rotor zones is so severe that it can cause structural damage to aircraft and has been responsible for numerous aviation accidents in mountain regions. Lee waves and rotors also affect surface weather conditions in complex ways. The strong downward motion of air in some parts of the wave pattern can create areas of clear skies and warm temperatures, while the upward motion in other areas can enhance cloud formation and precipitation. This creates patchy weather patterns where conditions can vary dramatically over distances of just a few miles. The interaction between mountain winds and moisture creates unique precipitation patterns that can vary dramatically over short distances. Windward slopes that receive the full force of moist upslope flow may receive hundreds of inches of precipitation annually, while these slopes just a few miles away may be arid or semi-arid due to the drying effects of downslope winds. This creates the dramatic rain-shadow effects that characterize many mountain regions, where lush forests on one side of a mountain range give way to deserts on the other side. convergence zones where different air masses or wind flows meet and interact, often develop in mountain regions due to the complex topography. These zones can create persistent areas of cloud formation and precipitation that remain in approximately the same locations relative to the topography. The Puget Sound Convergence Zone in Washington state is a well-known example, where air flowing around the northern and southern ends of the Olympic Mountains meets in the Puget Sound region, creating a persistent area of enhanced precipitation. The vertical structure of mountain winds adds another layer of complexity to understanding mountain meteorology. Wind speed and direction often change dramatically with elevation, creating wind shear conditions where adjacent layers of air move in different directions or at different speeds. These wind shear zones can create hazardous conditions for aviation and can also enhance or suppress the formation of mountain waves and other wind phenomena. Boundary layer effects become particularly important in mountain regions, where the interaction between airflow and the complex surface topography creates three-dimensional wind patterns that can vary dramatically over short horizontal and vertical distances. The boundary layer, the portion of the atmosphere that's directly influenced by friction with the Earth's surface, can be much deeper and more complex in mountain regions than over flat terrain. Mountain winds also interact with larger-scale atmospheric patterns in ways that can influence weather far from the mountains themselves. The Rocky Mountains, for example, can influence the development and movement of weather systems across much of North America by creating preferred pathways for storm development and by modifying the characteristics of air masses that flow over them. The seasonal evolution of mountain wind patterns reflects the changing thermal and pressure patterns that develop as solar heating changes throughout the year. Summer patterns may be dominated by thermal circulations driven by differential heating, while winter patterns may be more influenced by the passage of large-scale storm systems and the pressure gradients they create. Monsoon patterns in some mountain regions create dramatic seasonal reversals in prevailing wind directions and moisture transport. The North American monsoon, which affects the southwestern United States and northwestern Mexico, brings moisture from the Gulf of California and the eastern Pacific Ocean into normally arid mountain regions during the summer months, creating a distinct wet season that contrasts sharply with the dry conditions that prevail during most of the year. The interaction between mountain winds and vegetation creates feedback effects that can influence local climate patterns. Forest fires can create their own wind patterns through intense heating, while the presence or absence of vegetation can affect surface roughness and thermal characteristics in ways that influence wind flow patterns. Deforestation or afforestation can literally change the wind patterns in mountain regions by altering the surface characteristics that influence airflow. Human activities in mountain regions must constantly adapt to the complex and variable wind patterns that characterize these environments. Airport design and operation in mountain regions requires careful consideration of wind patterns, with runways oriented to take advantage of prevailing winds while avoiding areas prone to severe turbulence or wind shear. Building design and construction must account for wind loading conditions that can vary dramatically depending on local topography and exposure. Renewable energy development in mountain regions often focuses on taking advantage of the enhanced wind resources that result from topographic acceleration and channeling effects. Wind farms are often located on ridge crests or in mountain passes where topographic effects create consistently strong winds. However, the complex and turbulent nature of mountain winds also creates challenges for wind energy development, requiring specialized turbine designs and careful site selection. As we observe our air mass flowing through this complex landscape of ridges, valleys, and peaks, we can appreciate how the solid topography of mountains transforms atmospheric circulation from simple, broad-scale flow patterns into intricate, three-dimensional wind systems that are as varied and complex as the terrain itself. The winds have learned mountain ways, adapting their flow patterns to work with and around the obstacles presented by the solid earth. These mountain wind patterns represent some of the most beautiful examples of fluid dynamics in the natural world, where the principles of physics create flow patterns that are both mathematically elegant and visually spectacular. Understanding these wind patterns helps us appreciate how mountains influence weather and climate on both local and regional scales, and how the simple presence of elevated terrain can create atmospheric phenomena that affect conditions far from the mountains themselves. In our next exploration, we'll discover how the transformed air and complex wind patterns we've been observing create the conditions that support the remarkable forms of life that have evolved to thrive in the challenging but beautiful environments of high mountain regions. As we approach the culmination of our journey through the transforming atmosphere above mountain landscapes, we discover perhaps the most remarkable aspect of our exploration: how life itself has adapted, evolved, and flourished in the challenging conditions created by the atmospheric changes we've been following. The thin air, reduced pressure, cold temperatures, and complex wind patterns that define high mountain environments haven't created barriers to life, but rather opportunities for evolution to craft some of the most extraordinary and specialized organisms on our planet. In the alpine regions above the tree-line, where our transformed air creates conditions that would challenge most lowland life forms, we find plants that have become masters of efficiency and endurance. These alpine plants have evolved strategies that allow them to photosynthesize in thin air with reduced carbon dioxide availability, maintain cellular processes in intense cold, and withstand the powerful winds that are shaped by mountain topography. The cushion plants that dot many high mountain landscapes represent one of evolution's most elegant solutions to the challenges of alpine environments. Growing in tight, compact mounds that hug the ground, these plants minimize their exposure to drying winds while creating microclimates within their own structure that can be several degrees warmer than the surrounding air. The dense growth form allows them to share resources and maintain warmth through collective thermal mass, while their low profile keeps them below the most turbulent wind flows. Alpine animals have evolved equally remarkable adaptations to the thin air we've been exploring. The snow leopard, hunting in the Himalayas and other Asian mountain ranges, has enlarged lungs and heart chambers that allow it to maintain the oxygen supply necessary for the explosive bursts of energy required to catch prey in terrain where every breath contains less than half the oxygen available at sea level. Its thick fur and compact body shape help it conserve heat in the cold mountain air, while its large paws act like natural snowshoes, distributing its weight over the snow that accumulates from the moisture transformations we observed earlier. High-altitude insects represent some of the most extreme adaptations to thin air conditions. Bumblebees have been observed flying at elevations above 18,000 feet, where the air density is so low that the physics of flight seem to argue against their ability to generate sufficient lift. These remarkable insects achieve high-altitude flight through a combination of increased wing beat frequency, modified wing shapes, and enhanced flight muscle efficiency that allows them to extract maximum lift from the sparse air molecules available at extreme elevation. As our peaceful journey through the mountain atmosphere draws toward its gentle conclusion, we find ourselves back at ground level, but forever changed by our exploration of how the air we breathe transforms as it flows over the ancient peaks and ridges that rise toward the sky. The breath of air we followed from its origins over the sea to its passage through the highest mountain reaches has shown us that the atmosphere is not a uniform, unchanging medium, but rather a dynamic, responsive system that adapts and transforms in response to the solid earth encounters. The air that now surrounds us carries within it the memory of its mountain crossing, the cooling it experienced through adiabatic expansion, the moisture it released as clouds and precipitation, the complex wind patterns it learned as it flowed around and over the topography. Even though this air has returned to lower elevations where pressure and temperature conditions resemble those where our journey began, it has been fundamentally changed by its encounter with the mountains. Understanding these atmospheric transformations helps us appreciate the profound influence that mountains have on weather, climate, and life across our planet. The rain that falls in distant valleys, the wind patterns that shape local climates, the seasonal cycles that govern ecosystem rhythms. All of these phenomena are influenced by the way air changes as it encounters elevated terrain. As you prepare for sleep, let your breathing settle into the same natural rhythm that governs the great atmospheric circulations we've explored together. Feel each breath connecting you to the vast ocean of air that surrounds our planet, carrying with it the stories of every landscape it has crossed, every mountain it has climbed, every transformation it has undergone in its endless journey around our world. The mountain air teaches us about adaptation, about resilience, about the beautiful ways that both living and non-living systems respond to challenges and create new possibilities. As you drift towards sleep, carry with you the peaceful knowledge that you are part of this great atmospheric system, breathing the same air that has crossed oceans and mountains, participating in the endless circulation that connects all places and all life on our remarkable planet. Thank you for joining me on this gentle ascent through the layers of our atmosphere. If this peaceful exploration of mountain meteorology has brought you comfort, if the wonder of atmospheric science has helped ease you toward rest, I'd be grateful if you'd consider subscribing to Whispering Atom. Share your thoughts in the comments below. Where in the world are you breathing this transformed air tonight? And what aspects of our atmospheric journey spoke most peacefully to your mind? Sleep well, fellow traveler through the ocean of air. Let the patient circulation of atmosphere slow your thoughts into the rhythm of mountain breezes. Let the gentle pressure of air around you remind you of your connection to the vast atmospheric systems that embrace our entire planet. Let your dreams flow like air over mountains, finding new paths and forms, carrying you peacefully through the night toward the dawn of another day beneath our shared and ever-changing sky.